Welcome to the Power Electronics class. Myself B. Virnarayana, Senior Assistant Professor, Department of Electrical and Electronics Engineering. We are in second unit, AC to DC converters. In the last class, we are discussing the single phase, full wave, midpoint type converter with R and RL loads, and we also discussed continuous conduction mode of single phase, full wave, midpoint type control converter with RL load. So coming to this single phase midpoint type full wave control converter with RL load, here this is a circuit diagram. It consisting one isolation transformer whose secondary winding is provided with the center tapping and two ideal SCRs. Here we have the RL load, hence why the combination of resistor and inductor are connected in series, and the load is connected between common cathodes of the SCRs to the midpoint type or midpoint of secondary winding of the isolation transformer. So depends on the value of the inductor, this converter maybe operates either in continuous conduction mode or discontinuous conduction mode. If you have large value of the inductor in the converter, then the converter operates in continuous conduction mode. If you have the low value of the inductor, then it operates in discontinuous conduction mode, and depends upon the value of firing angle in continuous conduction mode. This converter operates in two modes, either rectification mode or inversion mode. If alpha less than 90 degrees, then this converter should act as the rectifier and it converts AC power into the DC. If you maintain alpha greater than 90 degrees, then this converter operates as the inverter and some power should be transmitted from load to the source. In previous class, we already discussed this continuous conduction mode and continuous conduction mode, and what are the output voltage and current waveforms for rectification for alpha less than 90 degrees and inversion for alpha greater than 90 degrees already discussed. In this class, we just go with the discontinuous conduction mode of this midpoint type control converter with RL load. So if you go through this discontinuous conduction mode, so when we are getting the discontinuous conduction mode, for low value of the inductor. Discontinuous conduction mode, which is simply represents like DCM, and continuous conduction mode like CCM. So here we are able to draw the output voltage and current waveforms for discontinuous conduction mode. So this will be able to correct whenever you have low value of L in the load. Coming to the operation of midpoint type control converter with RL load under discontinuous conduction mode. During the positive half cycle of the supply, here terminal A is positive and B is negative. Corresponding that T1 comes to the forward biasing mode and T2 is in the reverse biasing mode. At omega T is equal to alpha, we provide the gate pulse to the first SCR, then the SCR1 comes to the on state. If the SCR1 will be in the on state, then the upper half of the source voltage, that is VA0, is transmitted to the load and current flow through the circuit is given by this A plus, T1, L, R, O minus and A plus. In this way, the current flow through the circuit, and corresponding that there was some energy must be stored in the inductor and the output voltage simply equals to the VA0. So from alpha to pi, output voltage simply follows the VA0 due to the conduction of T1. So VA0 means this portion from alpha to pi, this source voltage VA0 is available across the load due to the conduction of T1, and there was some energy must be stored in the inductor like this, and you have low value of the inductor, and at omega t is equal to pi, even though the output voltage 0, the output current cannot be 0 due to the property of the inductor. The current lags to the voltage by an angle phi, and there was some energy must be stored in the inductor as in the form of electromagnetic field. So at omega t is equals to pi, even though output voltage 0, output current cannot be 0. So the energy stored in the inductor is discharges to the source through the same SCR. Hence why the conduction portion of the SCR1 is extended up to the instant where the energy stores in the inductor is completely discharges. So here this is the energy stores in the inductor is discharges here. So up to this instant the conduction portion of the T1 is extends, hence why this small portion of the negative voltage here, this portion is also available across the load. Hence why from alpha to this is the beta, which is beta is called extinction angle. That means the conduction period of the SCR is extends due to the presence of the inductor in the load side. That portion is simply represented by the extinction angle, which is represented by beta. So up to beta, T1 will be in the on state. See here, from this beta to pi plus alpha, both the thyristors are in the off state. Hence why there is no current flow through the circuit and there is no output voltage in the load. And during the negative half cycle, same terminal A is negative and B is positive, corresponding that T1 is in reverse bias, T2 is in forward bias. At omega t is equals to pi plus alpha, we provide the gate pulse to the second thyristor. Then the lower half of the source voltage is transmitted to the load through the thyristor 2. So the current flow through the circuit B plus, T2, R, inductive, resistive load, O minus, and like this. So whenever the T2 will be in the on state, the lower half of the source is transmitted to the load. Whenever the T1 will be in the on state, the upper half of the source voltage is transmitted to the load. Hence why when T2 will be in the on state, from this pi plus alpha to 2 pi, you blindly follows the VB naught. So here this is the VB naught, then we are having the output voltage from pi plus alpha to 2 pi is simply due to the conduction of T2, which will follows the VB naught. Okay, and again the energy must be stored in the inductor. Same at omega t is equal to pi, even though output voltage 0, output current cannot be 0. Hence why the conduction portion of the T2 is extend up to the instant where the energy stores in the inductor is discharges. So that discharging path will be depends upon the value of inductor. Hence why up to this pi plus alpha plus beta, you have T2 will be in the on state. Hence why the small portion of the negative cycle will be available across the load. Hence why from this pi plus alpha to pi plus alpha plus beta, T2 will be in the on state. And again in this instant both the thyristors are in the off state. Hence why output voltage 0. Again during the positive half cycle, again T1 forward bias, T2 reverse bias. Same at 2 pi plus alpha, if you provide the gate pulse to the T1, again you have the output voltage like VA naught, and again the energy must be stored in the inductor is charges and again discharges. Hence why a small portion of the negative portion will be available across the load due to the conduction of T1, and again charging, and again you have the output voltage like VB naught due to the conduction of T2. So here this is the output voltage and output current waveform under discontinuous conduction mode. In this discontinuous conduction mode, observe here T1 will be on at alpha and it goes to the off state before pi plus alpha. So the conduction portion must be lies less than 180 degrees. It's very important. If you go through the discontinuous conduction mode, the conduction angle of the each SCR is below 180 degrees. If you go through the continuous conduction mode, then this conduction angle must be 180 degrees. Gamma is equals to 180 degrees for continuous conduction mode and gamma is less than 180 degrees in discontinuous conduction mode. So if you have the large value of the inductor, for example, then large amount of the energy must be stored during the positive half cycle of the output voltage, and At pi plus alpha, the next SCR comes to the on state. Before that, if the outgoing SCR T1 is continuously in the on state due to the energy stores in the inductor, then we are getting the continuous conduction mode. Before the incoming SCR, if the outgoing SCR goes to the off state, then we will say it will be operates under discontinuous conduction mode. So here this is the current waveform. Observe here, always the current should be positive, hence why the current always flows from right to left. Okay. So here this is the output current output voltage waveform. If you want to draw the voltage across the thyristors, I just want to draw the voltage across the thyristor T1 from 0 to alpha. What is the state of T1? Forward bias. Hence why the small portion of the positive pulse will be available across the T1. Assume ideal SCR. Ideal SCR means there is no voltage drop during the on state of the SCR. So from alpha to beta, T1 will be in the on state. Hence why voltage across the T1 is 0. Next, from beta to 2 pi, SCR will be in the reverse bias. Hence why from this beta to 2 pi you have the negative voltage across the T1. And again from this 2 pi to 2 pi plus alpha, forward bias and on state. So like this the voltage across the T1 will be varies. Here this peak inverse voltage is defined as the maximum voltage is available across the SCR during the off state or during the reverse biasing mode. Reverse biasing mode means when anode is made negative and cathode is positive, then the SCR is said to be in reverse biasing. During that reverse biasing, whatever the maximum voltage is available across that SCR, that should be represents the peak inverse voltage, which is equals to minus 2 Vm. Why you are getting the minus 2 Vm here? Just if you go through this equivalent circuit, here you have this is the equivalent circuit of single phase midpoint type full wave control converter with RL load. For example, by applying KVL to this ABCD loop, what you are getting? This is VA naught and this is VB naught. So minus VA naught plus VT1 minus VT2 plus VB naught is equals to 0. I just want to find out the voltage across the T1. So what is the VT1 here? VT2 plus VA naught minus VB naught. Clear? So here if VT2 is on, then voltage drop across this T2 is 0. If VT1 is on, then voltage drop across the T1 is 0. For example, if this VT2 is on, then voltage drop across the VT2 is 0, then what you are getting here? VT1 is equals to VA naught minus VB naught. Here VA naught is written as Vm sin omega t and VB naught is equals to minus VA naught. So here Vt1 is equals to minus 2 Vm sin omega t. So minus 2 Vm sin omega t means whenever the T1 will be in the reverse biasing mode, the maximum voltage is available across the SCR during the reverse biasing mode is minus 2 Vm. That is simply representation of peak inverse voltage. And these are the output voltage, output current waveforms. And if you go through the average DC output voltage, V0 is equals to how many pulses you are generating here for completion of one full cycle? 2 pulses. So 2 by 2 pi integral. What is the duration of each pulse? From alpha to beta. From alpha to beta you have the output voltage. So the limitations are considered as alpha to beta. How much voltage you transfer? Vm sin omega t d omega t. Vm sin omega t d omega t. By simplifying this expression, what you will get? V0 is equals to, take Vm by pi, 2 gets cancelled. Integral sin omega t is written as minus cos omega t, and you replace the limits between alpha to beta, and finally you are getting V0 is equals to Vm by pi into cos alpha minus cos beta. This is the average DC output voltage during the discontinuous conduction mode of single phase midpoint type full wave controlled converter. And next one, RLE load. If you go through this single phase midpoint type full wave controlled converter with RLE load, especially in continuous conduction mode, there is no effect of the back EMF. There is no effect of the back EMF. And if you go through the discontinuous conduction mode, then where both the SCRs in the off state, then output voltage is 0. See here, from this beta to pi plus alpha, both the SCRs are in the off state. Hence why output voltage is 0. And from this pi plus alpha plus beta to 2 pi plus alpha, here also both the thyristors are in the off state. Hence why the output voltage is 0. So if you go through the discontinuous conduction mode, then where the output voltage is 0, then the back EMF is coming to the picture. Like this. Like this. Here. So here this output voltage is simply equals to the back EMF. And here also like this. So here also where both the thyristors are in the off state, then the output voltage simply equals to the back EMF. So if you go through the midpoint type full wave control converter with RLE load under continuous conduction mode, there is no effect of the back EMF. Simply the performance of that midpoint type full wave control converter with RL load and RLE load should be same. If you go through the discontinuous conduction mode only, then we have the effect of the back EMF, and where the output voltage is 0 in RL load, then the back EMF is coming to the picture and the output voltage will be redrawn like this. This is the simple representation of single phase midpoint type full wave control converter with RLE loads. And next, before goes to the single phase bridge type full wave control converter, what are the drawbacks of this midpoint type converter? In this midpoint type converter, the major drawback is the peak inverse voltage is minus 2 Vm. Depends upon the peak inverse voltage, the selection of the SCR will be depends. So if you have the peak inverse voltage is high, then the selection of the SCR must be high rating SCRs must be considered in the construction of the converter. So if the peak inverse voltage is 2 Vm, then you will select the rating of the SCR which is suitable to to withstand this 2 Vm voltage. That means large rating SCRs must be required to construct that midpoint type converter. That is the one drawback. Another drawback is in the circuit configuration you have the isolation transformer whose secondary winding is provided with the center tapping now, hence why the transformer design is difficult and the transformer utilization factor is very low of this midpoint type converter compared to the bridge type full wave converter. And see here we have source voltage is represents like 2 Vm sin omega t. If the source voltage is taken as 2 Vm sin omega t, how much voltage you transmit to the load? Only Vm sin omega t. So if you take 2 Vm sin omega t is taken as the input to the primary winding of the transformer, out of 2 Vm sin omega t we are able to transmit the load only Vm sin omega t. That means half of the power should be transmitted, hence why the rectification efficiency is also low. So to overcome these drawbacks, simply we go through the bridge type full wave control converters. We already discussed in the classification of the converters, the single phase full wave converters are mainly classified into two types, depends on the configuration of the circuit. Those are midpoint type converters and bridge type converters. Now we will go through the bridge type converters. So next classification of these full wave converters, single phase bridge type full wave control converters. Controlled converters. So depends upon the circuit operation. Again these bridge type full wave control converters are classified into two types, like single phase fully controlled converters, fully controlled converters or full wave converters, and second one single phase half controlled converters, or these are also called as semi converters. Single phase half controlled converters or semi converters. What is the difference between these two? Where we prefer the fully controlled converter and where we prefer the half controlled converter will be discussed in this class. So first we go through this single phase fully controlled converter, fully controlled converter with R load. Yes. Coming to the single phase fully controlled converter with R load, this is a circuit diagram representation. It consisting one isolation transformer, 4 ideal SCRs which are numbered as T1, T2, T3, T4 and resistive load. If we go through the midpoint type converter, it consists in 2 ideal SCRs and one isolation transformer whose primary winding is provided with the center tapping, and it has several disadvantages like the peak inverse voltage is 2 Vm, hence why the large rating of SCRs must be required. Another drawback is the transformer utilization factor is very low, and the third drawback is the design of that isolation transformer is difficult. Due to these drawbacks, to overcome these drawbacks of the midpoint type full wave converters, simply we go through the bridge type fully controlled converters. So coming to this bridge type fully controlled converter, it consisting 4 ideal SCRs and one isolation transformer. Here the function of this isolation transformer is isolate or separate the source and the load. So one of the major drawback of these power semiconductor devices, these power semiconductor devices are the harmonic generating devices. Harmonic generating means due to the switching condition of these power semiconductor devices, the harmonics must be injected into the source side. Due to these harmonics, the other components which are connected to the same source may be affected. So to overcome that problem, simply we are providing the isolation transformer. Hence why if during the switching condition of these power semiconductor devices like SCRs, if the harmonics are generated, then those are circulated into the secondary winding of the transformer. Hence why to prevent the harmonics injected into the source side, we are providing the isolation transformer. Coming to the operation of bridge type fully controlled converter with R load. During the positive half cycle of the source, here the terminal A is positive and B is negative. Terminal A is positive and B is negative. Corresponding that T1 and T2 are in forward bias. T3 and T4 are in reverse bias. Why? Because T1 anode and this is cathode. T3 is this is anode and this is cathode. T2 this terminal is anode and this terminal is cathode. T4 here it is anode and here it is cathode. So observe here, during the positive half cycle of the supply, terminal A is positive and B is negative. Corresponding that anode of the T1 connects to the positive terminal, so forward bias. Cathode of the T2 connects to the negative terminal, forward bias. Anode of the T3 connects to the negative terminal, reverse bias. Cathode of the T4 connects to the positive terminal, reverse bias. So during this positive half cycle, T1 and T2 are in forward bias, T3 and T4 are in reverse bias. At omega t is equal to alpha, we provide the gate pulse to the T1 and T2 by using some external firing circuit. At the same time, we provide the firing pulses to the T1 and T2. Then T1, T2 comes to the on state. If T1, T2 are in the on state, then the source voltage VAB is simply transmitted to the load and current flow through the circuit is given by from this A plus T1 resistive load, T2 B minus and source, like this. Here this is the current flow through the circuit. The current flow through the circuit is given by, observe here, A plus T1 resistive load, T2 B minus and source, and again like this. Here this is the current flow through the circuit. Hence why if you go through the output voltage waveform from alpha to pi, we provide at omega t is equal to alpha, we provide the gate pulse to the T1, T2. Here IC1, I2 represents, we provide the gate currents to the thyristor 1 and the thyristor 2. So from alpha to pi, T1, T2 are in the on state. If T1, T2 in the on state, simply you follow the output voltage VAB. So from this alpha to pi, the VAB will be represents like this. So that positive portion is simply available across the load due to the conduction of T1, T2. This notation is very, very important. And if you go through this one is the output voltage waveform. If you go through the current waveform, here you have resistive load now, hence why the current is in phase to the voltage. So this is the representation of I0, which is equals to the V0 by R. Which is equals to the V0 by R. Here this is the representation of output voltage and output current. So if you draw the voltage across the T1 from 0 to alpha, what is the state of T1, T2? Forward bias. Hence why this small portion of the positive voltage will be available across the T1, T2 during the 0 to alpha. From alpha to pi, T1, T2 are in the on state. Hence why there is no voltage across the T1, T2. T3, T4, reverse bias during the positive portion. Hence why this total positive voltage from 0 to pi is available across the T3, T4. Here the peak inverse voltage is minus Vm. Peak inverse voltage is minus Vm. This is the output voltage and output current voltage across the thyristor representation during the positive half cycle. And next coming to the at omega t is equal to pi, both the output voltage 0 and output current 0. After pi, negative voltage will be available across T1, T2. So T1, T2 goes to the off state or reverse biasing mode, and after pi, from pi to 2 pi, during the negative half cycle of the source voltage, see here, during this negative half cycle, terminal A is negative and B is positive. During the negative half cycle of the source, terminal A is negative and B is positive. Corresponding that T3 is in forward bias, T4 is in reverse, sorry, T3 and T4 both are in forward bias, T1 and T2 are in reverse bias. During the negative half cycle of the source, terminal A is negative and B is positive, corresponding that T3, T4 are in forward bias, T1, T2 are in reverse bias. At omega t is equals to pi plus alpha, we provide the gate pulse to the T3, T4. Corresponding that from pi plus alpha to 2 pi, T3, T4 are in the on state and the voltage VBA is nothing but VBA is equals to minus VAB, which is VBA is equals to minus Vm sin omega t. So that minus Vm sin omega t can be represent the mirror representation of VAB. Here this is the VAB na. VBA is nothing but minus VAB. Hence with the mirror representation, it will represents like this. This is the VBA and this is the VAB. So from pi plus alpha to 2 pi, we provide the gate pulse to the T3, T4. So VBA is transmitted to the load and the current flow through the circuit is see B plus T3 resistive load, T4 A minus and the source like this. Observe B plus T3 resistive load, T4 A minus and secondary winding of the transformer. In this way the current will be flow through the circuit, and if you go through the output voltage and output current waveforms here, from at omega t is equal to pi plus alpha, we provide the gate pulse to the T3 and the T4. So the output voltage simply follows VBA. So VBA means this portion from pi plus alpha to 2 pi. Hence why the output voltage will be like this. Here T3, T4 are in the on state. That notation is very, very important. And if you want to draw the current waveform now, so current waveform, here we have the purely resistive load, then the current is in phase to the voltage. And the magnitude of that current should simply depends upon the resistance. Hence why I0 is equals to V0 by R. And if you want to draw the voltage across the thyristors from pi to 2 pi, what is the state of T1, T2? Reverse bias. So from pi to 2 pi, the negative portion will be available across the T1, T2. Here also the peak inverse voltage is minus Vm. And from pi to pi plus alpha, T3, T4 are in forward bias. Hence why this small portion of the positive voltage will be available across the T3, T4, and pi plus alpha to 2 pi, those are in the on state. Hence why the output voltage across the thyristors T3 and T4 is 0, and again at omega t is equal to 2 pi, both the output voltage 0 and output current is 0. After that the negative voltage is available across T3, T4. So T3, T4 goes to the off state. Again from 2 pi to 3 pi, again we have the positive portion or positive half cycle, corresponding the terminal A is positive, B is negative, and T1, T2 are in forward bias, T3, T4 are in reverse bias. At 2 pi plus alpha, we provide the gate pulse to the T1, T2, and again the output voltage simply follows the VA0, and here simply we follows the VB0. Here again T1, T2 will be on, T3, T4 are in the on state. Again if you want to draw the current waveform like this one, and voltage across the thyristors 2 pi to 3 pi, reverse bias, forward bias, on state. So these are the output voltage, output current, voltage across the thyristors VT1, VT2, and voltage across the thyristors VT3 and the VT4. These are the output voltage, output current, and voltage across the thyristors. And if you go through the average DC output voltage here, average DC output voltage V0 is equals to how many pulses you are generating here? For completion of one full cycle of the source, here we are able to generate the 2 pulses in the output voltage waveform. So we will write 2 by 2 pi integral. What is the duration of the each pulse? alpha to pi. So alpha to pi, how much voltage you transmit? Vm sin omega t d omega t. So by simplifying this expression, what you are getting, V naught equals to 2 gets cancelled. Take Vm out of the integral, minus cos omega t. Integral sin omega t is minus cos omega t, and you replace the limits between alpha to pi. What you are getting here, V naught is equals to Vm by pi into minus cos pi. Cos pi is minus 1, minus of minus plus 1 plus cos alpha. So here this is the output voltage in case of this bridge type fully controlled converter with R load. Okay. Next, if you want to find out the RMS output voltage, RMS output voltage, same, Vrms is equals to 2 by 2 pi integral alpha to pi Vm square sin square omega t d omega t whole power 1 by 2. By simplifying this, take Vm square out of whole power 1 by 2, Vm into 2 gets cancelled, 1 by pi integral alpha to pi. This sin square omega t is written as 1 minus cos 2 omega t by 2 d omega t whole power 1 by 2. So what happened here, Vm into take 2 1 by 2 pi integral 1 into d omega t between the limits alpha to pi minus sin 2 omega t by 2 between the limits alpha to pi whole power 1 by 2. So by simplifying this expression, you are getting Vm into 1 by 2 pi into pi minus alpha, minus sin 2 pi is 0, minus of minus plus sin 2 alpha by 2 whole power 1 by 2. So finally you are getting Vrms is equals to Vm into pi minus alpha by 2 pi plus sin 2 alpha by 4 pi whole power 1 by 2. That is the RMS output voltage of fully controlled converter with R load. And here we are discussing the operation of single phase fully controlled bridge type converter with R load. Here this is the circuit diagram, and here we have the output voltage, output current, voltage across the thyristors, and average DC output voltage. V naught is equals to Vm by pi into 1 plus cos alpha, and here it is the RMS output voltage. And next, coming to this single phase bridge type fully controlled converter with RL load. Again the circuit representation. Yes. Single phase bridge type fully controlled converter with RL load. Here this is a circuit representation. Here it consisting one isolation transformer, 4 ideal SCRs and R and L. The series combination of resistor and inductor is considered as the load for this bridge type fully controlled converter. And you know, depends upon the value of the inductor, the converter is operates in two modes. One is the continuous conduction mode and second one is the discontinuous conduction mode. Here the converter is operates in continuous conduction mode for high value of the inductor, and the converter is operates in discontinuous conduction mode for the low value of the inductor. First we go through the continuous conduction mode operation. So if the bridge type fully controlled converter is operates in continuous conduction mode, we will discuss the output voltage, current, waveforms and the operation. And you know, depends upon the firing angle. If alpha less than 90 degrees, here we are able to collect the rectification operation from this bridge type fully controlled converter under RL load. And if we maintain alpha greater than 90 degrees, then we are able to collect the inversion operation from the same converter. So if alpha less than 90 degrees, we have rectification, then some power should be transmitted here from source to load. And if you maintain alpha greater than 90 degrees, here some power should be transmitted from load to source. Some power should be transmitted from load to source. How we will discuss? First we go through the rectification operation. Here I am assuming alpha less than 90 degrees, hence why at this instant we provide the gate pulse. So coming to this operation, during the positive half cycle, you know, T1, T2 are in forward bias, T3, T4 are in reverse bias. At omega t is equals to pi plus at omega t is equals to alpha, we provide the gate pulse to the T1, T2, hence why this VAB is transmitted to the load. So VAB is transmitted to the load from alpha to pi due to the conduction of T1, T2. And during the presence of the inductor in the load side, what happens? There was some energy must be stored in the inductor. Here the current flow through the circuit, here terminal A is positive and current terminal B is positive during the positive half cycle of the supply. Corresponding the T1, T2 are in forward bias, T3, T4 are in reverse bias. At omega t is equal to alpha, we provide the gate pulse to the T1, T2. So T1, T2 comes to the on state and the voltage VAB is transmitted to the load. And the current flow through the circuit is A plus T1, R, L, T2, B minus and secondary winding of the transformer. In this way the current will be flow through the circuit. During that process, some energy must be stored in the inductor. Some energy must be stored in the inductor. So that energy stored in the inductor is simply represents like this. Observe here, at omega t is equal to pi, even though the output voltage is 0, the output current cannot be 0, and the energy stored in the inductor is discharges up to the instant where the next SCS comes to the on state. Hence why up to pi plus alpha, we have some energy must be stored in the inductor, that is discharges to the source through the same thyristors. Hence why the conduction of T1, T2 is extends up to the instant where the next incoming SCRs are available. So up to pi plus alpha, T1, T2 are continuously in the on state. If T1, T2 are in on state, then this negative portion of the source voltage is available across the load. Hence why from this alpha to pi plus alpha, both these T1, T2 are in the on state as long as the energy stored in the inductor is discharges. See here, at pi plus alpha, we provide the gate pulse to the T3, T4. Already during the negative half cycle, T3, T4 comes to the forward biasing. Here at pi plus alpha, we provide the gate pulse to the T3, T4. So immediately output current shifts from the outgoing SCRs to the incoming SCRs. What is the outgoing SCRs here? T1, T2 which are going to off state. Incoming SERs means the SERs which comes to the on state. So here at pi plus alpha, the outgoing SERs are T1, T2 which goes to the off state. So immediately the output current transmits from T1, T2 to T3, T4. Hence why again the current flow through the circuit is rising in nature. If T3, T4 are in the on state, we follows the VBA. Which is VBA? This one. Again the output voltage is positive portion due to the conduction of T3, T4. Again same at 2 pi, even though output voltage 0, output current cannot be 0. Hence why that current will be again discharges to the same thyristors. Hence why the conduction of T3, T4 is extends up to the 2 pi plus alpha. Here this is the conduction of T3, T4. So between this 0 to alpha also the current will be discharges, and this negative portion of the source is available across the load due to the conduction of T3, T4. It's very, very important. And again same T1, T2 and T3, T4. Here it is T1, T2 and again here it is T3, T4. Again current charging, discharging, current charging, discharging. So this is the representation of rectification operation under continuous conduction mode for alpha less than 90 degrees. Observe here, always you have some magnitude. That means the current flow through the load never reaches the 0. Then that is the representation of continuous conduction mode. And if you go through the alpha greater than 90 degrees, similarly here also, at this instant, we provide the gate pulse to the T1, T2. So, this small portion of the positive half cycle or positive portion is available across the load from alpha to pi. And energy must be stored in the inductor is charges. See here from pi to pi plus alpha, the energy stored in the inductor is discharges. Hence why this negative portion of the source is available across the load. So from this alpha to pi plus alpha, T1, T2 are in the on state. T1, T2 are in the on state. Again charging due to the conduction of T3, T4, again discharging, charging, discharging. Here also discharging. So like this. Here this is the conduction of T3, T4 and again here it is the conduction of T3, T4. It is the conduction of T1, T2. So what we observe from these two waveforms, if we maintain alpha less than 90 degrees, some power should be transmitted from alpha to pi, that is positive portion in the output voltage represents some power P1 is transmitted from source to the load, and the negative portion of the source voltage represents some power should be transmitted from load to the source. So what is the resultant power here? P1 is greater than P2. So finally from some power should be transmitted from source to the load. Source is AC, load is DC. So finally we are having AC to DC, which is rectification. Similarly, if you go through the alpha greater than 90 degrees, from alpha to pi, only some small amount of the power is transmitted from source to the load, and pi to pi plus alpha, large amount of the power is transmitted from load to the source. Out of this, P1 is less than P2, so resultant power is negative. That means some power should be transmitted from load to the source. What is the load here? DC load. Source is AC. DC to AC means inverter. Inversion operation should be taken place. Here this is a simple representation of single phase bridge type fully controlled converter with RL load under continuous conduction mode. Okay, RL load under continuous conduction mode. So if we maintain alpha less than 90 degrees, we are getting the rectification operation, and alpha greater than 90 degrees, we are having the inversion operation. This is the output voltage, output current waveforms. And if we go through the average DC output voltage here, average DC output voltage V0 is equals to how many pulses you are generating for completion of one full cycle? 2 pulses. So 2 by 2 pi integral. What is the duration of each pulse here? Observe, alpha to pi plus alpha. Alpha to pi plus alpha T1, T2 on state. Already said, if you go through the continuous conduction mode, the conduction angle must be 180 degrees. 180 degrees means if you bring the T1, T2 at on state at omega t is equal to alpha, up to pi plus alpha, they must be in the on state. Hence why here the limitations are considered as alpha to pi plus alpha, and how much voltage you transmit? Vm sin omega t d omega t. So by simplifying this expression, 2 gets cancelled, take Vm minus cos omega t between the limits alpha to pi plus alpha. You replace the limits here, Vm minus cos pi plus alpha minus of minus plus cos alpha. So what you are getting? Cos 180 plus theta minus cos theta minus of minus plus. So finally you are getting V naught is equals to 2Vm by pi. 2Vm by pi cos alpha. This is the average DC output voltage. From this you conclude, if you maintain alpha is equals to 0, what you are getting? V naught is 2Vm by pi. If alpha equals to 90, V naught is equals to 0. If alpha equals to 180, V naught is equals to minus 2Vm by pi. It's very clear. From this firing angle, if you vary from 0 to 90, you are able to positive output voltage, which is varies from 2Vm by pi to 0. If you varies from 90 to 180, then the output voltage should be negative, that is 0 to minus 2Vm by pi. That means depends upon the alpha, we are getting either positive voltage or negative voltage. If you got positive voltage and positive current, that is from alpha lies between 0 to 90 degrees, then this is said to be first quadrant operation, which is called rectification operation. If you maintain alpha greater than 90 degrees then voltage is negative but current is positive, then this is said to be second quadrant operation, which alpha lies between 90 to 180. That is simply called the inversion operation. So if you go through this bridge type fully controlled converter with RL load, we are able to collect the two quadrant operations. Two quadrant means either first quadrant or fourth quadrant. Either first quadrant operation or fourth quadrant operation. Quadrant means this one. On V0 and I0, Vi plane. If you consider, this is the first quadrant, this is the second quadrant, and here it is the third quadrant, it is the fourth quadrant. At a time, if you want to collect the two quadrant operation means either first quadrant operation or fourth quadrant operation. If you maintain alpha less than 90 degrees, then you are able to collect the first quadrant operation. If you maintain alpha greater than 90 degrees, then we are able to collect the fourth quadrant operation from this bridge type fully controlled converter with RL load. So this is the output voltage waveform, output voltage expression. And if you want to find out the RMS output voltage, but we already derived in bridge type, simply you are getting Vm by root 2, that is equals to Vs. Simply this RMS output voltage should be simplified from this expression, like integral alpha to pi plus alpha Vm square sin square omega t d omega t whole power 1 by 2. By simplifying this expression, we already derived in midpoint type converters, the final RMS output voltage simply gives as Vs. So this is the representation of bridge type fully controlled converter with RL load in continuous conduction mode. So in this class, we just discussed the midpoint type converter with RLE load and bridge type fully controlled converter with R load and RL load. RL load we discussed continuous conduction mode and the discontinuous conduction mode. Thank you.